I've been working with Unix since about 1979 and started working with Linux in about 94, 95 after the court decision that said that my experience with Unix was no longer an issue when working on open source projects. I can't in any way give you a full introduction to what goes on inside Linux in 2 hours. So what I'm going to do is give you a bit of a history of Unix and Unix-like operating systems, including Linux, starting from Ritchie and Thompson back in the 60s, early 70s. Talk about the core concepts that are used to build a Unix-like operating system, and then talk about some work that I've been doing or have done over the last few years on scalability within Linux-like systems. So, what's going on here? What's happened? Oh, it's turned off. Stupid thing. Yeah. So, the story starts with Multix back in the 60s. Multix was a collaboration between Bell Labs, General Electric, and MIT, which was going to be producing the next generation of multi-user operating system. It was an all-singing, all-dancing system. The only problem was that they were designing the operating system before the hardware was ready. So after about 4 years of writing specifications and writing PL1 code that they couldn't test, Ken Thompson was really cheesed off. And so he talked to his manager and said, look, I can't do this anymore. And so his manager said, go off and do something different for a while. And he found a disused PDP-7 in a broom closet at Bell Labs and decided to port a space travel game to it. The interesting thing about this particular PDP-7 rather, is it had a graphical display unit attached to it. It was just a vector display. And so you could actually draw things on it. And so he thought this was really cool, and he started programming the space travel game. Unfortunately, to program that, he had to cross-compile from a Honeywell, which was in another building, and carry the paper tapes between the two buildings. This got old really, really fast. So we thought, okay, let's build a self-hosting operating system that's just enough that I can store my assembly code and compile it locally. So he and Dennis Ritchie, over a lunchtime, sketched out the file system on a whiteboard that was going to be the basis for Unix, and has still had the same concepts today. What happened was, in 1974, Ritchie and Thompson published a paper in the communications of the ACM. And at that point, everybody wanted to get at this thing, including the University of California at Berkeley and the University of New South Wales. Ken Robinson, who was a lecturer here in formal methods of all things back in the early 70s, wrote off to Bell Labs and got a copy of the tapes. At that point, the university had just put in a huge cyber system up the hill on top of the library. If you've ever noticed where there's 2 doors on the top of the library, that was to get the cyber in because it wouldn't fit in the lift. The other thing there is, if you've noticed at the top of the library, there's a kind of a metal bit all the way around. That was added when they put in the new airport radar, because when the radar came around this way, it caused the cyber to crash. Yeah, so we got those systems here, and in each department, they put a PDP-11, which was meant to be just a card reader to feed jobs to the cyber. What Ken Robinson and John Lyons realized was that this PDP-11 was also ideal for running Unix. So they put Unix on it and started using it for teaching. The people who did that work for coding up the card reader part that emulated what it used to do to talk to the cyber were Chris Maltby and Greg Rose. And they, of course, put in backdoors, so when they actually got to do the course that used that, their jobs would go to the front of the queue. Yeah. So anyway, what happened was that as Unix was only distributed as source code to source code licensees around the world, people would modify it for local use. And then they would share the patches that they developed to other places. This was before the days of the internet, so the way you shared things was by taking tapes from one place to another. And at the University of Berkeley, there was a guy called Bill Joy, and they had a first meetup of Unix users. This was about 1975. And Bill Joy spent all night copying tapes with all these patches on and distributed them. That was the first Berkeley system distribution. The main additions above standard Unix were a new teletype driver from UNSW and the X editor that Bill Joy had written. There might have been one or two other things on it, but they were the main additions above the standard Unix. And that was handed out to all the Unix users who met at the University of At the same time as the University of California was building up their Unix expertise, the Unix systems group within Bell Labs wanted something that they could use for writing patents, for preparing patents, document processing. So they wrote a thing called NROF, which was a document processing typesetting tool. And they trained all of their typists to use the X editor and the command line on Unix to write patent applications. Of course, when you put a system in general use in a place where there are lots of really, really bright people, they start modifying and changing it and doing what they want with it. The nice thing was that the core values of Unix were you have little tiny programs that you can easily compose using pipes. So it's fairly quick to write, say, a spell checker just by taking all of the documents you know that are properly spelt, sticking them through a pipeline to split them into individual words, sort them, extract so you've got unique words, and then you've got a set of unique words that are all correctly spelt. And then when you've got your document which you might not be correctly spelt, you can do the same process to it and then do a comparison to find out which words are in this document which contains possibly misspelt words that are not in the dictionary of correctly spelt words. And at that point, you can do it. And that's just a full-line pipeline to do. So it's pretty cool. The other thing that USG did was start to commercialize Unix because everybody wanted it. But they got so big and so many people wanted this that they started falling foul of the anti-monopoly laws in the US. So a typical Bell Labs salesman would come into your office and say, here's what you get if you get Unix. You get this pile of tapes, no support, and a bill for $10,000. That didn't stop Unix going everywhere. And places like Stanford, good students there spun off Sun Microsystems to build and port Unix to their variety. They were all over the place. People were spawned, little tiny companies were spawned off that designed computers, put Unix on it, and spread it around the world. John Lyons had it here, and for some reason the rule against copying the source excluded for educational purposes. So what he did was print it out in a book and handed it out to all his students. He also spent a sabbatical at Bell Labs in 1976 when he wrote a commentary on the Unix Level 6 source code, which went through line by line and explained what each function and line did and gave an idea of how it all fitted together. And he used that in teaching operating systems through till 95. I was his PhD student just before he retired. And one of my jobs was marking, because what he did was every 2 weeks, he would give an exam on the bit of the text they covered that so far. And that was on a Saturday, and it would have to be marked. And unfortunately, the course got really popular. When he started, maybe had 50 people. By the time I was helping him to mark it, it had 350. So we needed lots of people who actually knew what they were doing to mark all the work. I remember one time he wrote out some sample answers, and the sample answer sheet got mixed up with the papers, and I marked it, and it didn't get 100%. Because he'd missed something that I'd picked up from somebody else's proper answer. So that was kind of interesting. Anyway, the John Lyons book was suppressed by Bell Labs. They said, okay, you're not allowed to distribute it anymore. But it was the core for the operating system that lots of people were using in binary form. So it tended to get photocopied, same as that, and it became one of the most suppressed computer science books in history. UNSW got some kind of an exemption, so they carried on using it for their courses until John died, retired just before he died from ill health. Yeah. But what happened after the suppression, after the inability of Unix source licenses to be given out cheaply to universities, was most universities around the world stopped teaching operating systems in any depth. The one standout apart from that was Andy Tannenbaum's group in Amsterdam. He developed an operating system with his students called Minix, which was a system call compatible with edition 6 Unix. And then he used that for teaching. In 1991, Linus Torvalds came along and he had some fundamental disagreements with the way that Minix was structured and thought, okay, I'm going to write my own operating system. After all, how hard can it be? And that's where Linux started. Now, the basic concepts within Unix were really well established very, very early on. The model that objects are owned by users and processes act on behalf of users. So you need to authenticate yourself and then a process acts on your behalf to do things. The idea of a process being an address space plus a thread of control running in it. The idea of the file system, which split the idea of naming from the idea of the file from the contents of the file. The other really novel thing within Unix was that a file was just a stream of bytes. It had a beginning at byte 0 and then went on to its size, then stopped. Before that, file systems implemented structured files. And one of the most common structured file was just card images. So you have 80 columns and it just looks like a deck of cards. They also had things like index sequential access method files, so you could specify a file with a record and an index field, and it would build an index for you so you could scan it in various different orders. And all this stuff, Unix didn't do any of that. A file was just a string of bytes, and any semantics was imposed by user space. That was novel for the time. The other thing that was really well established early on was the interprocess communication mechanisms. Essentially, pipes and the so-called MERT operating mechanisms. MERT was another real-time operating system that was experimental at Bell Labs at the time, and it had semaphores, message queues, and shared memory. And if you ever wonder why the IPC in Unix looks so different from everything else, it's because it was imported from another operating system and just bolted on the side. Very few people, apart from databases, use the MERT mechanisms anymore. But they were standardized by POSIX later on. So that was what we had in edition 6 Unix. When Unix was first converted into C, it started getting ported. One of the very first ports was to the Interdata 832 at Wollongong University. The interesting thing there was that Richard Miller and Professor Reinfelds started out by writing a compiler. They didn't have a tape drive, so what they had to do was drive up to Sydney, to here, cross-compile their compiler, put it onto a disk pack that could be read by the Interdata, here, drive back to Wollongong, put it onto the machine and see if it worked. This was slow, but it only took 3 iterations, I think, before the compiler worked. And at that point, they started developing locally on the Interdata down in Wollongong using the previous operating system to bootstrap into the new operating system. There's an interesting article in Organ volume 14, number 4, from Tony McGrath, who was involved on that very first port of Unix. He is still around. He works in Wollongong still. So, yeah. So, well, what's going on here? Oh, this stupid thing. So other things got added. Multix was one of the very first that had pages as opposed to a base limit register for their memory management unit. So the PDP-11 used a base limit register. When the University of Berkeley ported Unix to the VAX, which was a 32-bit machine, it had paged memory. So paged virtual memory was added in 1979 in edition 3, the Berkeley distribution. One of the interesting things about that particular one is that it had a bug in the timer driver, which caused whenever the timer overflowed, which happened about once every 4 hours, the machine would crash. Yeah. Yeah. TCP/IP was a new thing developed by ARPA, and unlike Multix, where they built shells full and shells full of documentation before they wrote a line of code, DARPA developed TCP/IP in exactly the opposite way. They produced a sample implementation that they tested and got to work, and then wrote it into a standard. And the University of California at Berkeley did that, and they put TCP/IP networking into BSD 4.1 in 1983. And that's where the internet really started. The killer app at that time was email. The web didn't come until sometime later. And multiprocessing. We had multiprocessing back in 1984 from the Sequent Balance, which was running on the National Semiconductor 16032 processor. It was interesting in that it had a special external bus for doing collision detection. And it's a wired or bus, and when you wanted to talk to the data bus that connected between the processors, you'd put your ID onto the wired or bus and then read it back. And only one of the processors would win, because you'd all be fighting as to which bits you were setting. So that was pretty cool. Sequent did an awful lot for developing Unix systems. They gave out scholarships to promising people and prizes, including to this university, for outstanding work in operating systems and in embedded systems work. So, unlike SEL4, which only abstracts a tiny bit over to provide IPC and threads, Unix provides a lot more abstractions. The core abstractions are files, threads of control, and the memory space. And of course, the user model that it provides permissions for all of those. The way that things work is by inheritance normally. This thing's really annoying me. The process model, it starts with a handcrafted process at boot time called init, which typically just runs a user process that starts everything else, then waits for it to stop. And then init calls fork, which makes an exact copy of the address space. Now, fork was a really nice thing back in PDP-11 days, which was a 16-bit machine, so the maximum amount of data you needed to copy was 128K, 64K of instruction space and 64K of data space. And the way that fork worked was it didn't bother copying the instruction space, just the data space, and it would just arrange for it to be copied out to disk into swap space, and then returned with a 0 value to say that I'm running in the child. And then when it swapped back, it just swapped the other stuff back in, and it carried on. So it only took about 4 lines of assembly to implement fork. Nowadays, of course, with threads of control and huge processes, it's become a much less attractive mechanism for creating new processes. In particular, it takes a long time to copy all those page tables, especially on a large 64-bit address space. The idea is that as far as possible, you share everything with your parent and inherit things from your parent, and then before you call exec, you can use the standard system calls to adjust things, to open new files, to close old files, and so on. And it allows a process to control what is shared. There's also in Linux, there's a clone system call that gives you much finer grained sharing, control over what actually gets shared with your child, and you can use that for creating threads. And POSIX introduced a new thing, POSIX spawn, which combines fork and exec. But it's a bit harder to use because you need to specify just about everything about the new process in the POSIX spawn system call. So a process clones itself by calling fork. Almost everything is copied, the address space, the permissions, the open files, all of that stuff. But some attributes are shared. Any segment you've marked map shared will be shared with your child, and open files are shared with your child. Now that's really useful. You know how in the shell you've got this if then else statement? They used to be separate commands, and they knew which file descriptor the shell script was on. So if would then fork and exec its argument, and if that returns 0, it would just return, and the shell would keep on reading. Otherwise, it would seek until it found the else, and then it would return. And so a separate program could implement if and then, if then else, which I think is pretty cool. How file descriptors work. When you open a file, you get a file descriptor, which is a small integer, which indexes into an array which is attached to your process. The file descriptor table contains just two things. But one of them is a pointer to an open file descriptor. The open file descriptor contains an offset into the file and a pointer to an in-kernel inode, the index node that describes the file that you're reading from. If you then call dup, you just get another copy in your file descriptor table of the pointer to the inode. If you then call fork, the file descriptor table is copied, but both file descriptors will point to the same file offset table. And then if you call exec, some of those will be closed. So a typical way of creating a new process within Unix and Unix-like things is this code here. You switch on fork. Fork returns 0 in the child and the process ID of the child in the parent. You then close your standard file descriptors and duplicate the ones you really want to have input, output, and standard error file descriptors. And then you call exec. If exec fails and you come back to yourself, then you're dead. So you may as well exit. In this case, we exit with an underscore to say don't flush the buffers. Don't do a sync on your file descriptors because we're sharing all those file descriptors with the parents and it can do it. If you get a -1, you've got an error. Otherwise, we'll just wait for the process. Each process has an exit status. By convention, a 0 exit status means I succeeded in what I did. Anything else means something went wrong. So you can just wait and do things. The problem with fork, as I said, it was almost perfect in the original system, but now address spaces are huge, so you need another mechanism. And there's lots more state in a modern system. All those sockets, all that other stuff, graphics contexts, you name it. And so it becomes a lot more unclear what you need to copy. Also, when you copy a multi-threaded process, only one thread will be copied. But locks held by the other threads will still be taken, which means it becomes a much less useful abstraction. The permissions model is based on logged in users. A user is represented by a small integer, 16 bits at the moment. And every user is given a primary group ID as well. In original Unix, you were only a member of one group at a time, and you had to use the new group command, which was a privileged command, to move to a new group ID. Berkeley 4.3, I think it was, it might have been 4.2, introduced the idea of auxiliary groups, so you could be in multiple groups at once. And that's the model that's currently used. It used to be you were restricted to up to 16 groups, but now I think that limit's been removed. So you can be a member of as many groups as people want to configure. This is mostly for file access, but it can also be used for IPC. The file model separates names from content. The regular files are just bytes, I've already said this. But devices and other things are also represented by files in the file system. So there's whole file systems called /proc and /sys that contain things that look like and act like files, but do stuff. So every process in a Linux system is represented by a directory in /proc that contains information about that process that you can find out. This was actually stolen from Plan 9 operating system, which was a successor to Unix developed at Bell Labs. In Plan 9, the way that you do a fork is by copying bits out of the /proc process ID file system into another one. So, yeah. Directories are just files that contain name to inode mappings. Originally, there was only one file system kind, and so that file format was the only one that was understood by the kernel and was used to look up name to inode mappings. Nowadays, we've got dozens of different file systems. There's an extra layer of indirection added, and each file system provides its own version of name lookup. If we look and try and parse /bin/ls, say, you start off at /, which is the root of the file system, and then you scan down until you find bin as the name. It's inode 324. So you go and read inode 324, and it's another directory. So then you read through it until you find ls. It's inode 301, so then you open that, and that gives you your file. Name_i is the routine that is used to translate from name to inode. As I said, now it's abstracted by BFS layer. It is a bottleneck. It used to be one of the main bottlenecks. Chris Maltby, whom I mentioned earlier, is in the Unix Hall of Fame for adding a cache for the name_i to inode mapping into Edition 6 Unix. It's still a bottleneck today, even with caches of all over the place. The nice thing, though, is it hides the boundaries between file systems. So when you mount a file system into a directory tree, you don't need to worry about it. You can just continue to use path names to find things. That's unlike things like MS-DOS or Windows, where you've got a drive letter and then a colon and then a file path within that volume. You don't need to worry about volumes anymore. So when you use name_i, it just walks the path name, as I showed you before, translating symbolic links on the way. A symbolic link is where instead of an inode in the directory, you've got the name of another file. So if we go back here, you can have multiple names with the same inode in them. Each name inode pair is called a link, and they're the hard links within Unix. They all refer to the same inode. So obviously you can't have hard links across volumes because inode's a namespace per volume, per file system. So if you want to be able to link and create aliases for a file on that volume over here, you need to use a symbolic link instead. So what I'm going to tell you here is the evolution process is basically KISS. Keep it as simple as possible at first, and then as you have better hardware, as you've got new requirements, add in the capabilities to do the newer bits. So when you start, it's really easy to show correctness, it's really easy to implement, and you can try things out and make sure they actually work the way you want. If it then becomes a bottleneck, you can go and change it. So an awful lot of the commands we've got in Unix now originated as shell scripts, as very simple shell scripts, a lot of them. And as that became a bottleneck, they were re-implemented in C or some other language. So as you find drawbacks and scalability problems, add new ones. Now, that's all Unix basics. Now we're going to move into Linux itself. If you ever look inside the Linux kernel, it looks like C, and it is almost C. It's C extended with some extra keywords and some extra macros. So you've got some section IDs, __init, exit per CPU, and so forth. These mark out data elements and functions that are only needed at particular times. So if a data item is labeled __init, or a function is labeled __init, it's put in a segment of the program that will be discarded after the system's booted. Or if it's in a module, it'll be discarded after the module is loaded. _exit says we're only going to use this when we unload this module. So if you're going to have a driver that's built in, anything labeled _exit can be discarded at link time. And this gives you a less memory usage when you actually run the system. And if you look in a Linux boot log, you'll see discarded so many kilobytes or so many megabytes just before it drops to user space. We've also got a rudimentary model checker built into the build system. So you can mark pointers as being user pointers, which have been handed in via a system call, or kernel pointers. And the model checker will make sure that you do a transformation to make it safe before you access any data via a pointer that's labeled user. And it makes sure that you can't actually hand a pointer that's labeled kernel back to user space. There's also RCU and IOMEM for stuff that's controlled using the recopy update algorithm, which I'll come to right at the end of this lecture, or is used for I/O. The problem with IOMEM is it needs to be mapped uncached so that you can get to it at the time you use it. There's also locking annotations. Normally, if you take a lock, you'll release it in the same function. There's occasions when you actually want to split that and have lock and release of lock in two different functions. The model checker will check normally that you acquire and release a lock in the same function, and all the paths through the function, every acquire is matched with the release. If you've got your acquire and release in two different functions, you need to tell the model checker that. So you say it acquires the lock and releases the lock. And then it will know that it's meant to release the lock on all paths, or it's meant to acquire the lock on all paths. And there's extra types checking for engine portability. So if you've got an external memory location that's got to be little endian and you're running on a big endian machine, or the other way around, you can specify that it's bitwise. And then the compiler will, and the model checker will force you only to access it via a routine which will sanitize the bits to be the way around they're supposed to be. We've got some extra features and iterators. Inside the kernel, it's very object-oriented. And anytime you've got a type that's a compound data type, like a tree or a list or anything like that, there will be an iterator associated with that tree or whatever. So you've got these iterators that you call for each, and it will then iterate over every entry and do the right locking, pointer following, or whatever has to happen to be able to follow it. That's used for things like abstracting over the page table abstraction for different hardware. We've also got container of for if you've got an object that sits inside an object, container of will go from the object that's inside to the container object. So you can get the pointer of the PCI structure, PCI device structure, from a device that's on the PCI bus, for example. And there's macros to register object initializers and destructors and lots of things like that. It uses inline functions as much as possible rather than C macros. It tries to use ifdef as little as possible. If something's ifdef'd out, then the compiler won't check it for syntax as it's going along, or semantics. If it's guarded by if some expression that evaluates to 0 at compile time, the compiler will still check it's consistent and correct, but it will then eliminate it before you get to the link phase. So rather than use ifdef whatever in the kernel code itself, it tends to define feature test macros, which can then be used in a standard C-if statement to control which bits get into the final kernel. Internally, it has to have some abstractions. So the three things that it abstracts are the MMU, so that it can run on things that are weird, like the power series, which have got an inverted page table, or all the hierarchical page tables like Intel and ARM, and so on. The memory consistent model. I don't know whether you've looked at cache hierarchies and cache consistency models within a multiprocessor?
In previous course.
Good, good. Well, every architecture has got its own memory consistency system. One of the weakest is the alpha, DEC alpha. One of the strongest is Intel x86 hardware. Linux provides its own memory consistency model. And again, there's a model checker in there that makes sure you put barriers of the right sorts in the right places so that when you build the thing, those barriers will be translated into the appropriate barriers for the system you're running on, and it will still work. There is a whole heap of what they call litmus tests, which are little programs of what can happen if you run these two bits of code in parallel with these barriers in place, according to the memory model of Linux. And inside the Linux source tree, those are there, and there's a set of scripts that will run those against an SMT solver to show which outcomes are possible, so that you can actually validate that your SMP code is correct. The device model I'm going to talk about a little bit more. But first, I want to talk about scheduling. schedulers, Linux has had lots of different schedulers in its time. The first one was just a very, very simple round-robin thing, but it was quickly discovered that that didn't really work for interactive use. It was easy for long-running batch processes to starve interactive use, so you ended up with really poor response times when you were typing. And a guy called Con, who was actually an anaesthetist down in Melbourne, spent a lot of time trying to work out why the Linux scheduler was so bad. So what you want is something which is order 1 in the number of runnable processes, so it doesn't get slower if you've got more processes to run. You want it to be fair in some sense. That is, you don't want any process to be starved, and processes with similar nice should get similar amounts of time, assuming they've got similar demand. You want really good interactive response. You want it to be topology aware, and I'll come back to that. And you really want the scheduling part to be order log n or better in terms of the number of runnable processes. So dispatch should be fast. So when you want to say, okay, give me the next process, that should be order 1. But when you actually make more scheduling decisions, that should be no worse than order log n. They're the desirabilities. The first one, the process changes from time to time. So currently, it's the so-called completely fair scheduler by Ingo Molnar. The way this one works is it keeps its processes in a red black tree, ordered by amount of virtual runtime that has run so far. Virtual runtime is a number between 0 and 1, which represents how much time the process has had recently, or the thread has had recently. And it's scaled by the nice of each process. As processes run, you always choose the leftmost on the tree, which has got the least virtual runtime so far. You run it for a time slice or until it sleeps, whichever's sooner, and then add the amount of runtime it's had back into it and then put it back into the tree. If this works properly, all of the processes will, over time, converge on the same amount of virtual runtime going along. It's got some not completely fair bits, in that in order to keep the numbers bounded for virtual runtime, it has to be scaled all the time. And that advantages processes that want more time. You also want to give good interactive response, so when something wakes up from a long sleep, which is effectively what you get when you're typing something, it's a relatively long time between keystrokes, the process is given the v runtime of the least runtime so far, so it'll run fast. For short sleeps, where it's just a millisecond or two, it'll just keep its old v runtime and carry on going. So that's how that one worked. It's interesting to see how the one before that ran. It had this dual entitlement scheduler. So the idea here is that you have got two queues, the deserving queue and the undeserving queue, the running queue and the expired queue. And you give each thread a time slice according to some algorithm that you've worked out. And then you run each one until it runs out of time slice or it goes to sleep. If it goes to sleep, that's fine. If it wakes up and it's been only a short time, you stick it back into the running queue. Otherwise, you stick it in the expired queue. When the running queue is empty, you work out what the time slices are for all of the expired ones and then swap the queues. And that was what was used before the current completely fair scheduler. It also has the probabilities of fairness. But if you've got a lot of processes running and your interactive process gets sucked in the expire queue, interactive response is really poor. So I mentioned topology aware. Sorry, no, this is what I was talking about with the, this is the completely fair scheduler. I think I've said all that stuff. The devil is really, really in the details. You need to be able to keep recent history to know which threads have just had a short sleep and which ones have had a long sleep. You need to control where things run. After you've run on a particular core, the cache in that core has got your data in it. If you get rescheduled on a different core, it's got to populate its cache from the previous cache, and that's slow. So you really want to repopulate the same cache that you had before. You also want, if possible, to keep cores busy so you can shut down other cores for power management. If you've got too many threads, it becomes expensive to maintain these structures. So what do? Sleeping tasks. When a task sleeps for a long time, if you give it back its original V runtime, then it's going to perturb the complete fairness of the scheduler. And finally, group hierarchy. Control groups exist in Linux to provide containerization. And what you want to be able to do is divide up your CPU time so that everything in the group competes with other things in the same group, but different groups compete with each other. So this container competes with that container, but within each container, the threads compete with each other. And so all of this stuff needs to be added on to that fairly simple system that I described. And it gets quite complicated quite fast. In terms of scheduling, the entities you've got to schedule on are your thread of control, your hyperthread, which are divided into a core, and these individual cores share cache. Your cores are into packages, and packages get put into NUMA nodes, each with its own chunk of memory. It's actually more complicated than this, because within a package, you've got multiple connections to different bits of RAM, and so even within a package, you can have a NUMA architecture. And what's more, the bandwidth of each channel between RAM and package varies, depending on which one it is. Some of them are bidirectional and the same in each direction, same bandwidth. Others are unidirectional, so it costs more to read than it does to write. And likewise, the interconnects between caches. And so it gets really, really complicated to try and know what that stuff is and then schedule it correctly. So to simplify it down, it's best where possible to reschedule on the same processor so you don't move your cache footprint. Linux allocates memory on a first touch basis. So what large multi-threaded processors do is they'll spawn all their threads, and then each thread will start touching the memory that it uses, so it will have memory that's close to it. And MPI does that, for example, for multi-threaded things. If you can't schedule on the same processor, you want to schedule on one that's close to it, so in the same package. Or if you can't do it on the same package, on the same node. Or if you can't do it on the same node, on a node that's nearby in the NUMA topology. And if you can, keep whole nodes idle so you can power them off. If you can't keep whole nodes idle, whole packages idle. Power management has become one of the big things in data center computing because the power costs so much. Every watt you generate within a computer, you need to take away with the air conditioning, so you pay twice. If you can identify cooperating threads, then you want to schedule at the same time using a gang schedule or group scheduling type approach. And that's quite difficult sometimes. So as you can see, the scheduling becomes quite complicated quite fast. So the way it works is that each real or logical processor, we've got logical processors, is given a separate queue. And you arrange those queues in a hierarchical domain. And you do load balancing. If a thread becomes idle, and there's no work for it to do, the idle thread on that one looks at its nearest neighbor and looks to see if there's anything in that queue. And if there is, it steals it. If it can't steal it from there, it'll try and steal it from the next one over, and so on, to try and load balance from the bottom up. And if you can, keep whole domains idle. Memory. Linux memory management is a bit weird because Linux was first put onto an IBM PC with 640K of memory. Back in those days, the 90s, the key bus was an ISA bus, and the ISA bus could only DMA to the first 16 bits of data. So you've got this DMA region up to 16 meg, which is the region that the ISA bus could DMA to. And any time when you want a buffer that you can DMA to, that you want to allocate to a device driver, you have to allocate it in that region. Then you've got your normal region up to 900 meg, and then there's a gap in the PC address space, and then every other bit of memory is high memory. So what Linux does is it takes the low 900 meg of memory and allocates it above the 3 gig binary, above the kernel. And anything in that zone, you can allocate just using a simple offset. The rest, you can't. So the direct map pages, they become logical addresses in the Linux kernel that you can access with PA and VA. So PA just converts from virtual to physical, VA to physical to virtual within the kernel address space. Small memory systems have all of the memory down there, but you find almost no systems nowadays with less than 1 gig of memory. Even the smallest have got 2 gig, and one of the machines we're working on has got 1 terabyte. So if you've got more memory, when more memory systems came about, they changed the kernel to refer to every bit of memory as a struct page. It's misnamed, it should be a struct frame. But the idea is that you've got a physical address, possibly a virtual address where it's mapped in, and a few bits of metadata about it. A struct page has got up to 10 words, and I say words advisedly. It's 32-bit words on a 32-bit machine, 64-bit words on a 64-bit machine. It contains a few flags. It contains the backing address space, a pointer to the backing address space, which is the inode that represents the file this thing is mapped from. For anonymous memory that isn't mapped from a file, there's a special inode that's provided by the kernel that pretends to be a file for the purpose of generating anonymous pages. It's got an offset within that mapping, so offset 7 would be the 7th 4096 byte chunk in a file. It's got reference counts because you can have the same frame mapped into multiple address spaces. And if it's mapped into the kernel, it has the kernel address space. So this is what it all looks like from the point of view of a task. You've got the struct task struct, which has a pointer to a struct memory struct, MM struct. If you've got more than one thread, they're chained off the struct task struct, and they all point to the struct MM struct. The struct MM struct will point to one of those as the owner of the address space. If that one dies and the other threads are still going, the pointer will be updated to point to the next one in line. The struct MM struct also points to the page table, which is abstracted according to what sort of hardware you've got. And it has a pointer to a list of VM area structs, each of which corresponds to one call to mmap when the process was created. When you're doing exec, it does a virtual mmap for the text area, for the data area, for the BSS area, and for all the shared libraries and for the stack. So each of those would refer to one of those. Each of those then points to a struct address space, which is a misnomer. It's a description of the backing store for that mapping. And as I said, that can point to a file, or it can point to swap, or it can point to the special anonymous dev0 inode. So that's the structure of how it all fits together. As usual, the devil's in the details of maintaining all this stuff. An address space then is a collection of pages mapped from the same object. It tracks the inodes that it maps from, and it keeps a radix tree of all the pages in the mapping. That allows you to look things up fast. And it's got an operations vector, just like any object would, for doing things like marking a page as dirty, so it will be scheduled for page out at some point, for populating frames into the backing store, for cleaning pages. When you type sync at your command line, write pages will be called on all of the backing stores that are available. Migrate pages from moving pages between NUMA nodes, and that's now called automatically after a thread has moved to somewhere that's far from its original location. After a short time, if it doesn't kill itself and it keeps on touching pages, migrate pages will be called to move the things around. And there's a heap of other housekeeping which is less interesting. So at page fault time, the kernel looks up which address is being faulted. If it's in the kernel, it does special things. Normally that involves a panic because the kernel is not meant to be paging. Unless the kernel is trying to access memory that belongs to a user space thing, in which case it will arrange to get that paged in. Then it will find the VMA, the struct VM area struct for that address, and will introduce a segmentation violation fault if it can't find it. If it's a stack and the address that you're allocating is within one page of the current bottom of the stack, it'll just extend it, allocate another page. Otherwise, it'll check permissions and do a segmentation violation if the permissions fail. So if you're writing to a read-only segment or trying to execute in a section that's not mapped to executable. And then it will call Hartle-MM fault, which walks the page table to find the entry. That walk will populate higher levels in the page table if it's needed. And then eventually we'll call handle PTE fault with the page table entry that it's discovered to populate that page table, which will also call the backing store to read the stuff in, allocate a frame, and do whatever else is needed. So it does a lot of work at page fault time. So a Hartle PTE fault will look at the page table status. The kernel's got this clock algorithm that goes through and marks pages as not recently used. At that point, when you get a page fault, all you need to do is flip the present bit in the page table, which will then mark it as recently used again. Otherwise, it can provide an anonymous page. It can do copy on write processing if you've mapped this thing copy on write from a fork. So it can just allocate a new page, copy it, and then you're done. You can reinstantiate the page table entry from the page cache if it's there, or it can initiate a read from the backing store. And if the page table entry gets changed, it needs to flush that part of the TLB because currently there's a negative entry in there so that it can carry on. I'm getting so annoyed with this. Device driver interface. I said I'd come back to this. There are three kinds of devices in Linux. There's platform devices. There's devices on buses that you can enumerate, like PCI device. And there's devices on buses that you cannot enumerate, like SPI devices, that you need to know about ahead of time. Platform devices. Okay, firstly, I'm going to talk about numeral buses, because these are the core, the common sort that's used everywhere. Every enumerable device driver has a table that tells the bus driver which devices it can handle. So here we've got something which the PCI table, the defined PCI table is a macro that not only has the right type for the table, but it also puts it into a place in memory where it becomes as part of an array that the PCI driver can search. And then it says that this particular one's for Realtek 8139 and for a TTTech MC3222, the same device driver table, the same device driver can drive both of them. So the module device table takes that and puts it into the array. When the PCI driver scans its bus and discovers one of this sort, it will then call the probe routine for this driver. When it calls the probe routine will go out and find out, is there really a device there of this kind? Because one of the stupid things that some manufacturers do is they make multiple versions of a device and put the same device ID and vendor ID in, even though they're completely different things underneath. So the driver has to do a bit more work to work out, is this really an Ethernet driver? Or is it something else? So that's what happens here. When the device driver is initialized, it calls init to register itself with that operations table. It can call exit to deregister the driver on unload time. And the probe returns 0 if the driver claims the device. Then depending on what sort of device it is, it might also have open, close, read, write, or send message, receive message for an Ethernet driver, or whatever. If you've got something which isn't if you've got a platform device, this is for the Slug, which is the platform that was used for advanced operating systems about 8 years ago. You've got the ID here is Plat 8250 dev platform, and there's a static structure that describes this in a file that is in the architecture-dependent ARM code that says this is what it is. When it has this, this will be treated as this. Will also be put into an array, and it will then be treated as an enumerable bus of platform devices, and the device driver for each one will be called the probe routine. Nowadays, we tend to use a device tree to do this, and so instead of being hardwired into the kernel like this platform device, they will be obtained from the device tree. And that will tell you where the device is, that it has, 2 memory locations, and they're at these 2 resource locations. So for non-enumerable buses like SPI, you treat them exactly the same way. You just put an entry in the device tree, which will then generate that code, and then when the device tree driver enumerates the devices in there, it will call each driver that has registered itself as handling a particular device. So the device tree describes a board plus all the peripherals that are implemented for it. Device trees were originally introduced as part of the open firmware specification for PowerPC, but they're now used generally for any system that doesn't have an ACPI table to tell you where things are. On Intel systems, the information is derived at runtime from the ACPI table, plus well-known devices like the serial ports, which are always at exactly the same place. But for other things, it's in the device tree, which describes the layout of your device plus all its peripherals. It replaces the ACPI tables. The names in the device tree then trigger the device instantiation. So this is what a serial port might look like for the AM Logic Meson 6, which is the thing that's on the Odroid Cs that you're using for your projects. It says it's compatible with an AM Logic Meson 6 UART and an AM Logic Meson UART and a few other things. It has a register at memory address OX84C0, which is OX18 bytes long. It uses that interrupt on that gig. And the status OK means this thing really is present and we want to use it. The way that the device trees are normally laid out is you've got a generic one that is for the SOC that has all the possible devices. And then for a particular board, you've got a board level version that includes that and has this bit with just status equals OK in it, because the status will be disabled in the original one. And the idea there is that if you've got, say, some pins that could be a UART or a PWM device or an SPI, and it's wired up on this board to an SPI controller to a temperature sensor, and on this one to a UART, then only one of those will be enabled in the board device tree, even though both of them are present in the SOC device tree. So, I thought I'd better have a very brief word about containers because they're so big now, things like Docker. I mentioned group scheduling. You can also have groups for memory and everything else. So it does namespace isolation just like Chroot did. Chroot's been in Unix since the very early days. But this does more namespaces, not just the file system namespace, but also the process ID namespace and the user ID namespace and so forth. So you've got a separate namespace for each container, plus memory and CPU isolation, plus other resources as necessary, like networking. And with that, you can isolate and control and schedule all of your resources per container, and the containers can fight each other. And that provides a very light way to do pseudo virtualization. It's pretty neat. Play around with it. The two main technologies are Docker and libvirt and LXC. The LXC stands for Linux containers for doing this stuff. It provides a very easy way to quickly create a virtual operating system environment that you can play with. So I've got ones on my thing for CentOS, Red Hat, Ubuntu in various flavors, and Debian in various flavors. So I can test the instructions for installing SEL4 on all those different platforms. And you put these in a hierarchy. And that's what you use it. Anyway, I've told you the status today. It changes fairly quickly. Most of the things I've told you about have been fairly stable for the last several years. But I don't know when someone's going to come up with a new scheduler or some new way of using the new technology that's coming on, like the Optane or the NVRAM or whatever. So it could be different next week. Look at the source. It's all open source. And I've also simplified an awful lot. There are lots of heavy details. So what I want to talk about now is scalability and some work that I've done on Linux scalability. Because you'll understand Linux runs on everything from very, very small MMU list microprocessors up to machines with more than 4096 processors. And getting it to scale is a challenge. So some fraction of the operating system cycles can't be used for applications. There's always operating system code paths, there's intercache coherency traffic, there's memory bus contention, there's lock synchronization. There's lots of things where you can't give all of your cycles to user space. And in particular, the intercache coherency traffic and memory bus traffic gets in the way of scalability. So if you've got a process or some job where some part of it can benefit from being on multiple processes, but some part of it is just serial, then the speed up you get is given by Amdahl's law, which is this thing here. So if your T sigma is the amount of time that you spend that you're serialized, which means that the time 1 minus sigma is the time that you can spend that can be sped up. So you can run the time that you can speed up on all of your processes at once. And if you've got row processors, then the overall speed up is given by this function here. And that's Amdahl's law. Amdahl was famous both for his law and for stealing IBM's operating system and starting a company to market IBM 370 clones. Anyway, Amdahl's law. If you think about what that means in practice, you get a picture that looks something like this. You're going to have applied load on the bottom. That might be packet requests per second coming in. You've got your throughput going up the side, which is requests that have been fulfilled per second coming out. And there are 3 parts of this graph. The first part is where you're not overloaded. So the speed at which you get things done is based on the speed at which you can give the thing work. Every time you give it some work, it does some work and then sends you back the result. This could be, a web request. I send an HTTP request, get a page back. When you get to the next bit, you're starting to get packets, requests arriving before you finish the previous job. And so you start getting this curvature. When you get to the straight bit, you're going flat out. And there's enough work coming in to keep you busy all the time. You're at 100% CPU. And so there's no way for the processor to go any further. If you then add new processors, what you want is a straight line. What you often get is it goes for a little while and then then it collapses. If you look at the latency curve, that's what you want. You want the straight lines, but you get the dotted ones. If you look at the latency curve instead, it's this black hockey stick. The latency is constant, which is basically the time that it takes to do the work, until it starts getting overloaded, and then it becomes possibly infinite. So then we come to Gunther's law. Neil Gunther is an Australian who worked with SGI in Adelaide, in Melbourne. And he said, what we have to account for this, this fall off at the end of the scalability graph, we're going to introduce a new term, beta, which is an n-squared term. So we've got Amdahl's law, which is just that bit there, and he adds this term here. And that corresponds to crosstalk between different functions within your parallel system. So it's coherency traffic or contention on something. If we have a look at some numbers, if you've got alpha and beta equals 0, you've got perfect scalability and the line just goes straight up. If you have alpha greater than 0, beta equals 0, then you get the curve that we saw before, our good scalability curve where you've run out of things that you can parallelize. If you put beta greater than 0, you start getting the fall off. Let's try and look at some what that might look like. If you've got a very simple queuing system, you've got arrivals come in, some distribution might be Poisson, might be something else, and then you've got a server that's got an average service time, and so it just looks like that, and that's really easy. But we've quite often got something that looks more like this, where you've got 2 queues and 2 processors. So for this one here, might be your interrupt handler for the Ethernet driver. And this one here might be your web server. So at this point, if you've got lots of load coming in, this process here, running at a high priority, starts taking all the time and stealing it from your web server, which then cannot make any forward progress. And that gives you that forward, that fall off. In this case, the contention is for the processor between two processes that are running on the same processor. Let's have an example. This is Postgres using TPCC benchmark. And you'll see that it's got a peak at 5,000 queries per second, which then drops down and pretty fast and goes. If you do your mapping onto alpha and beta, you get something like this. You can see that that is not a perfect curve. It's a fairly poor fit. But you do see that beta is non-zero, so you're looking for contention in your system. If you think about how a database works, your obvious point of contention is your write-ahead log. Competing writes onto that with writes on your actual data, because you've got to do writes to your commit log, then to your data, and then to the commit model log again, and that's going to cause the disk to seek. So let's try putting the write log on a different disk. At that point, we get this throughput instead. And you'll see it's much better. We haven't got that droop. We've still got something happening here, right? There's still something happening there, but I don't know what it is yet. The most likely thing, by the way there, is the file system itself getting in the way. ext4 is known for problems when you've got multiprocessors with contention on the write log when you get more than about 4 processors, and this we're running on a 12 processor system. So another example, this is AIM7. AIM7 is a benchmark that models a heap of students all doing little compiles and edits and so forth, the kind of thing they used to do when you had a large multi-processor computer with lots of people doing things. What to note here is that the performance is still going up when we get to 50 clients, but the 12-way is below the 8-way line. So we've got negative scalability there. Now we've got to find out what the contention is. And what I did was I ran a program called LockMeter, which looks for contended locks in the system. So I'm looking for contention, and I find one. Here, have I got it in red? No, I haven't. Let me go back to that one. What's happened here? I'll find this. Yeah, here we go. What we can see is that in the find lock page, there's 2 calls to a lock. And in the first case, when it comes in there, 86% of the time, there's no waiting, and 30% of the time it spins. But then when it comes in and locks again, 85% of the time it hits a spin lock. And that's going to slow things really down because it's really contented. If we look at the code, it looks like this. We've got a spin lock on the mapping tree lock, and then we're going to lock the page before going on and doing some more stuff that we need the mapping tree lock locked for. So releasing that lock, and then when you try and get it again, some other processes come in and gone through the same cycle and hit the same point. And so you end up spinning a lot on that lock. So what we do is replace the spin lock with a reader-writer lock and see what we get. Now we can go up to 16-way, and we've got much better scalability. And you can see that the distance between the curves is much more even. It's still a little bit different between that distance there is less than that distance there. Let's put those two side by side so you can see. Note the difference in scale. We've got a 10 times improvement in throughput just by changing a spin lock into a read-write lock. This actually does hurt performance on a two-processor system, but not as much as it gains performance on the larger systems. And with systems now, two-processor, it's hard to find a two-processor system nowadays. So this got into Linux as a result of some patches I submitted upstream, about 10 years ago now. So that's interesting. So tackling scalability problems, first you've got to find the bottleneck. That's not always easy. Then you've got to fix or work around it. That's not always easy either. And whenever you do try and fix the bottleneck, you need to check that the fix you put in for the bottleneck on your system doesn't make it worse somewhere else. So you've got to check that your scalability fix for the big machines doesn't break performance on the small machines. And then you can experiment with different algorithms, different parameters. The big thing at the moment for scalability and performance is cache, locality, and coherence. So that is the area which I generally look at first for what's wrong with performance issues. And restructuring your system to avoid caching problems and cache collisions and problems where you move a process to a different processor and then you've got cache traffic between the two all the time. That's one of the places you often have to look at fairly early. So you experiment with different algorithms. There's a whole class of algorithms called, what are they called? Cache neutral algorithms that are meant not to care about the layout of your cache and how many ways it is and where it is on your systems. And so, cache oblivious algorithms, sorry. So it's worth experimenting with those algorithms. It's also worth experimenting with locking things that don't require you to use memory barriers, or not as many, or getting away with lock-free algorithms, because locks tend to become bottlenecks. So finally, scalability problems are just like an onion. Quite often when you peel off one layer and fix one problem, it opens up another one underneath. And what's more, that one that you come across, in some cases, is worse than the one you just fixed.
So it's also like an onion in that it makes you cry when you peel away the layers?
Yes. Yeah. So how can you avoid doing locks? Well, one way is if you've got something which is inherently racy, let the race happen, detect it at the end, and if you've got a race, go back and do it again. And that is often quicker than putting a lock in the first place. So the other way is to allow safe concurrent access without excessive serialization using RCU or something like that. So let's look at a simple sequence lock, which is essentially allow races to happen, detect them, and then fix them. And then I'll talk about read copy update. The idea with a sequence lock is that readers don't lock at all, but you want to guard individual writers from both writing at the same time. And it looks something like this. You've got a volatile variable called seq, which just then means sequence. And on a reader, you just take a copy of the sequence, and if it's odd, you just spin until it's not odd anymore. You then do a read memory barrier to make sure that the invalidate cache is flushed, and you're in your case where you can be sure that the state that you've got is correct. You do whatever you wanted, and then check to see that the sequence that you got last time is the same as the sequence you've got now. If it is, then no race has happened and you're fine. If it isn't, then you just go and do it again. This algorithm is used, for example, in maintaining the time. The way that Linux does time is there's a pair of variables which have got the current clock time, and when you do a get time of day, it will read those using this mechanism to make sure they haven't been updated, and then interpolate using the current value of the cycle counter in your system to work out what the current time in nanoseconds is relative to that time. Because you've got several different variables that need to be updated in sync, the current clock time and the current value of the cycle timer, you need to have some way of keeping them in synchronization. What the writer does is it does the spin lock, it adds one to the sequence, so now it's odd. It then does a write memory barrier to make sure that write is visible to all the readers. It then does whatever it needs to do, does another write memory barrier to make sure that everything that is written is flushed to the cache, is visible to everybody. And then it increments it again, we're now even, and then unlocks the spin. And so you can see that the writers and the readers can race, but if the writer races, then it'll be detected by the reader, and the reader will go through and read again and get a consistent set of values. And that's much, much faster than using a spin lock or an atomic variable. Okay, any questions about that? These are used all over the place wherever you have a reader that needs a consistent view of some data, and a writers where you've only got one writer at a time, and you've got relatively few writers compared with readers. Okay. The other thing to look at is RCU. Paul McKenney invented this as back in the early 2000s, and he wrote his PhD on it. It's one of those things that is really, really obvious in hindsight. And I coded things like this and never called it read, copy, update. The observation is, if you've got some sort of linked list or other data structure where you've got pointers, and you've got threads running through them, and you want to change one of the things in the middle, if you want to stop all the threads from running through, it can be quite expensive. So what we're going to do instead is we're just going to update this is for a delete. We're just going to update the previous pointer, so new threads coming along will skip the one that's there, and things that are still in there will still be able to keep on traversing the data structure. If you're going to be updating that one instead of just deleting it, you would make a copy of it, update it, and then link it in, and unlink the other one at the same time in a way that works like this. You unlink it, and then after you've finished, when you know that there's nothing else in there, you can then take it away and delete it entirely. So what you do is keep a pointer to the things that you've deleted and stick them in an array. And then when all the threads have returned to user space, you know that there can't be any more threads running along any data structure. So at that point, you can run through your list of things that need to be freed and free them all. So it's really, really obvious when you think of it. Well, that brings me to the end of my talk. There's a few things here. Those are the read, copy, update ones. There are more things. When I put up the talk, I'll put up a version with notes of everything that I said, and then at the end there's a bigger bibliography, including the Richard Thompson paper and other things for you to have a look at, and you can look at the papers and see what things going. It's also got a link to the organ, which I said had the historic edition with interviews from Greg Rose, who was one of the people here who did the fair share scheduler and the improved device driver for teletypes back in the early Unix days. and from Tony McGrath, who was involved in the first Unix port in Wollongong, plus a few other bits and pieces that I passed on the way past. Do you have any questions before we go on? Okay, well, that's it then. Enjoy yourself. I was expecting this to take a little bit longer. I must have gone a bit faster than I expected.
So there's a lot of information.
Yes.
Yeah, there's a lot of information. But you'll be able to go through it again, because, and I don't think this is examinable, it's just for fun. So.
You said this used to be like 3 hours?
Yeah.
What else would you normally cover?
Put in. I had more details about the way that the Unix philosophy, about how you have multiple small things with a text interface between them. I had more information about the history of the Unix file system. So for example, you've probably seen there's /bin and there's /user bin and there's /var bin and there's /user local bin.
Yeah.
That all comes from history. In the original system, they had a small, well, by about 1 megabyte, fast drum, which was used during boot phase, and a much slower disk, which was a bit larger, it was about 10 megabytes, which couldn't be mounted at boot time. It had to wait till user space was up. So everything you need for fixing the system if it goes wrong, like FSCK, and for booting the system is in /bin. And everything that you need for running the whole thing is in /user. When Solaris came along, they wanted to be able to have diskless workstations or very, very small disk workstations, and then a humongous file server that provided things. So they introduced yet another variation. Var is for the things that vary from machine to machine. User is now the things that are on every machine exactly the same. And /bin is the things that you need for booting. And so they introduced /var. And user local was things that didn't come from the operating system vendor, but was installed by the local sysadmin. So that's why it's there. We've now got to the stage where disks are so big and so fast that what Linux does is, instead of having a separate partition, it puts everything into the init RAM disk that you need to boot. And there's also enough stuff in there to fix the system if things go wrong. And so distributions like Debian and Ubuntu are beginning to get rid of /bin and put everything in user bin. In the early days also, the administrative tools that you currently have in /sbin were in /etc, and sbin didn't exist. But later on, they wanted to be able to mount /etc read-only, so that nasty people couldn't get in there and change things, and so they put it into /sbin instead. Yeah. Okay. But things like that were in there.
Yeah. Something I've always kind of wondered about, but never quite got around to looking into. How do device files actually, how are they implemented?
Okay. Well, you know how when you do a system call, it goes into the kernel and then has to do something. Well, if it's a standard file, it will call into the file system to say, do this, to do a read. If it's a device node, the operations vector points instead to the device driver.
Right. Yeah.
So it's just a different object class.
Yeah, okay, so this is a different
Yeah.
function point for...
Yep. And the same for the files in /proc or /sys.
Yeah.
Yeah.
And also, like, with in /proc, you've got, like, proc self. How does proc self, like, end up,
It's magic.
always pointing to the current?
It's magic.
Yeah.
The kernel knows what the current process is,
Yeah.
and so it can always make that mapping to the current process, whatever it is. It isn't actually a link. It's just it's a separate directory that does things. Just like dev stood in and dev stood out and dev stood are magic. Yeah. Mm. But it's pretty straightforward. It's almost trivial to add new files to /proc in the code. There's machinery there that you just call, and it sets it all up for you, and you just need to provide a routine to be called when you call read and a routine to be called when you call write on it.
Right. Is that something that actually, like, gets used often in terms of adding?
Yes. Yes. It's a very easy way to add new functionality for experimentation. So, for example, I added, when we did user-level device drivers some time ago, I added a directory in /proc for each possible interrupt source in the system, which then, if you had the right privileges, you could sleep on it. You could open it and try and read. And when an interrupt came, you'd be woken up and allowed to carry on. So you could have a thread waiting on an interrupt in user space. So you can do that kind of thing. You could have done that with a device as well, a device node. But there didn't seem to be any matching device nodes that I could find that were reasonable. And it's a lot more machinery to set up a device node than it is to set up a /proc entry. Yeah. One of the other things that's been happening is that where the original Unix wanted to make everything just read, write, and open and close as far as possible. So you can do that on files, you can do it on teletypes, you can do it on disk block devices and so forth. But sometimes you want to be able to do things that you can't do via open, close, read, write. So for example, for a tape, you might want to move to the next tape mark. And so they needed to add these extra function that bypass that, the IOCTL, input-output control thing. The problem is that bypassed everything and quickly became the way to tell the kernel to do anything you wanted. And it became a real mess. So Plan 9 switched to devices as directories. So instead of a device node, they've got a directory node with something for reading, something for writing, and something for each control you can do, where you write a text command to do the control. And that's the model that's used in /sys. And more, the calls that used to be IOCTL to do things to devices have become read and writes to files in /sys. So you can get rid of IOCTL and just use read, write, open, close. Yeah, nice. Okay. I hope you enjoyed that.